Okay, for this, I want to go to a little bit of a history, but the key aspect of understanding how light microscope works, especially not the geometric optics, but the true fundamental limitation of a microscope. I said the fundamental limit of light microscope or any microscope we uses a wave as a medium. Okay, so there comes a Ernst Karl Abbe. Abbe was the person who first recognized and formulate and propose a theory of image formation. So let me first describe, for those who have maybe physics experiment in your middle school, high school, you remember you have a diffraction grading. Grading, what's interesting is it's a regular pattern, periodic pattern. If you send the light, then not only there is a primary light passing through, depending on the gradings period, the another light, diffraction light, will go the other direction, the other direction. This we call first order diffraction. But there are also second order diffraction and third, etc. So you remember that this diffraction grading, the angle difference really depends on the grading period. And he actually extended this basic idea of grading that, hey, we have learned about Fourier series analysis, that any wave pattern can be decomposed as a sinusoidal waves of different wavelength. Likewise, any of the object outside of the world, we can consider it as a composer superposition of gradings. So this might sound a little weird, but this is a fundamental insight into understanding the object. And we want to have an optical element or optical system to grab that information onto your screen. Let me reiterate. So you remember that grading pattern, if the grading is bigger, remember the diffraction when I explained, when the wave interact, the relatively, it's a bigger object, the bending of the light is not that big. However, if the relative grading space is much narrower, what happens? The bending will be bigger. So what it means is the information of geometry of the grading period actually reveals the bending of the light. The smaller the feature, the bigger the bending of the light. So if we can capture the bigger angle with the optical system and grab them into the image space, we can achieve higher resolution. If the grading is coarse, then the bending is smaller, and we grab that information with the optical imaging system or lens, we can get that information. Hey, wait a second, what about really tiny, tiny, tiny grading? That tiny grading will lead the light to bend more to high angle, then our optics may not capture them, then in the imaging space, we lost them. That's why we cannot image or get the information of very fine grading or fine feature, so we have a limited resolution. So that concept can be described here. So an object can be considered as a grading, and you send the light wave, and of course the diffraction order of 0 pass through, but there are first order plus minus diffraction and second order diffraction. But our lens is a finite, that let's say in this case, we lose the m plus minus 2. This is a higher order diffraction, and then these 1 plus 1 minus 1 will eventually form an image plane. So what that means, we may lose the higher order diffraction coming from fine, smaller features of the object. That's why our microscopic imaging has a limitation in terms of spatial resolution. And probably in the future, I will offer another class of biomedical optics. And at that time, you may grasp even more fundamental quantitative way, but this is what I want to explain you. Object can be considered and sum of gratings, and grating will diffract light, so that diffraction nature fundamental limit our finite size length cannot grasp high order diffraction. That's why those are coming from fine feature, and you cannot reproduce fine feature in your image plane. That's why we cannot image too tiny object, in fact, tinier than the wavelength of the light in general in our image plane. Okay, so that microscope image formation was recognized in 1873 by Abi, and his looks like this. And he was the first, if you look at history, he was a very interesting person, also made like a modern concept of a labor. So he made his workers in his company very well. So that's another of his contribution. But fundamentally, when he died, this is what into his tombstone. So D is in fact optical resolution. Resolution is proportional to lambda. Okay, so it's proportional to the ruler of the light, which is wavelength lambda, but it's divided by n times sine theta here, alpha. Remember, n sine alpha I will discuss. This is called numerical aperture. You see this angle alpha actually means this angle of acceptance to the length. So if the angle is bigger and bigger, then this sine alpha will be bigger, and so D becomes smaller, and you can image a smaller object or higher resolution. Okay, so if you name this theory, actually this is a quotation. So his insight for comments on the images. The microscope image is the interference effect of a diffraction phenomena, because these are diffraction phenomena, and these different diffracted light has to interfere onto your image plane. And so this famous theory we call diffraction theory. And this sets a fundamental limitation of resolution. So let's say we are using visible light, which is a several hundred nanometer wavelength. We cannot go below half of the wavelength as a resolution. Okay. So this one, so you can think of, hey, what about I'm using IR wave to do some imaging, and you can check out, oh, IR, are you using 1 micron wavelength? You can quickly think, oh, you may not be able to get below 500 nanometer resolution. Okay, so what if you can think of, oh my gosh, I'm using electron microscope. What's the resolution? Then you can think of, hey, electron is a particle, but electron can be considered, also contains a wave nature. That actually led to Nobel Prize, right? Wave nature of the electron. And so electron can have an exquisite resolution because it's 10 picometer to 10 nanometer. So you remember, electron microscope gives us a very good spatial resolution. So that led to the concept of numerical aperture, which I will show you n sine theta next. And that sets the resolution limit of a microscope. This was 1873. So for the past about more than 100 years, we were just talk about this idea. But it was only until the early 2000s that people are coming and to say that, hey, we may overcome this diffraction limit if we use a trick. Okay. For example, if we can focus light even smaller than diffraction limit in object space, then we can potentially have that resolution. Hey, if we can have a nice pattern onto the object where the pattern size is smaller than the wavelength, then we can get that resolution. This actually led to the discovery of breaking the diffraction limit of a light microscope, so that now we can have not only 100 nanometer resolution, we can have tens of nanometer resolution. And of course, that led to the Nobel Prize of 2014 in chemistry. So, it's very important to understand the fundamental limit. It's even more important to think of where comes that fundamental limit and how to break that down.